Let's be honest. You and I rarely look up at the stars anymore. In our cities, a constant wash of artificial light obscures them from view. And even if we could see them, our focus is usually captured by the screens in our hands. We seem to have no time for what we might dismiss as such trivialities. If it weren't for the tireless work of astronomers, those dedicated few who periodically interrupt our news feeds with findings most of us find baffling, we might have collectively forgotten the stars even exist. Observing the cosmos can radically shift your perception of the world and your role within it. When you truly grasp the sheer scale of the universe, many of your daily troubles and anxieties can begin to feel far less significant. This practice cultivates a sense of humility, a deeper respect for nature, and a more considered way of living. It serves as a powerful reminder that you are a component of something immeasurably vast, with a chance to help understand and protect our small corner of it all. If you're looking for a place to begin your observations, the magnificent star Sirius is an excellent choice, as it's the most brilliant star visible in our night sky. You can find this easily identifiable star within the constellation Canis Major. Its incredible brightness is primarily because it is so close to us, a mere 8.6 light-years from Earth. The light you see from Sirius has traveled for 8.6 years, at a speed of about 300,000 kilometers per second to reach your eyes. And the star itself shines with 25 times the luminosity of our own sun. While Sirius is certainly a very luminous star, countless others in the cosmos are far more powerful in absolute terms. The reason they don't outshine Sirius in our sky is simple. They are much farther away. Their immense distance, combined with intervening cosmic dust that can obscure their light, means that from our vantage point on Earth, they appear significantly dimmer than our brilliant, relatively close neighbor. To locate Sirius for yourself, start by facing south, which is its general location in the northern hemisphere's sky. Your best guidepost is the famous constellation Orion. Look for the unmistakable pattern of 3 bright stars in a row that make up Orion's belt. Now trace a line from that belt downward and to the left, and your gaze will land directly on the most brilliant star in that area. That's Sirius. The winter months offer the best viewing conditions when the star is high above the horizon, but a stargazing app on your phone can also guide you to its precise location in real time. You might confuse Sirius with the planet Venus, as both are exceptionally bright, but a few key differences make them easy to tell apart. Sirius, a star with an apparent magnitude of -1.46, will appear to twinkle intensely, and can even flash different colors, like blue, due to atmospheric diffraction. In contrast, Venus, a planet, shines with a steady, brilliant white light, and has an even greater apparent magnitude, ranging from -3.8 to -4.9. Most importantly, Venus is always found close to the horizon near the sun, appearing as the morning star before sunrise, or the evening star after sunset, while Sirius can be seen at various times high in the night sky. What you see as a single point of light is actually a binary star system. The brilliant star visible to the naked eye is called Sirius A, and it is accompanied by a tiny, dim companion known as Sirius B, which is a white dwarf. Astronomers in the 19th century deduced the existence of this companion without ever seeing it. They observed that Sirius A wobbled on its path through space, as if it were orbiting an unseen object, leading them to conclude that a second star's gravity was pulling on it as they both revolved around a shared center of mass. To understand this concept, think of the center of mass as a system's perfect balance point. Imagine you have two apples of different sizes tied together by a string. The balance point won't be in the middle but will be closer to the heavier apple. If you were to hang the string from that specific point, the two apples would hang perfectly level. In the same way, the two stars in the Sirius system, Sirius A and Sirius B, do not orbit each other directly, but rather both revolve around this common invisible center of mass. This knowledge is fundamental, as it allows astronomers to decipher the movements of stars within binary systems and other celestial groupings. Through sustained observation and analysis, it has been confirmed that Sirius is, in fact, a two-star system. The average separation between Sirius A and its companion, Sirius B, is about 20 astronomical units. To give you some perspective, 1 astronomical unit represents the mean distance from our Earth to the Sun, which is approximately 149.6 million kilometers. Sirius B, however, travels along an elliptical path, meaning its distance from Sirius A varies dramatically. At its closest approach, known as periastron, it comes within just 8 astronomical units, while at its most distant point, or apastron, it reaches a separation of 30 astronomical units. To help you visualize this, if you were to place Sirius A where our Sun is, Sirius B's closest pass would be somewhere between the orbits of Jupiter and Saturn. At its farthest, it would be out near the orbit of Neptune. On average, the distance between the two stars is comparable to the orbit of Uranus, which circles our Sun at an average of 19.2 astronomical units. Although Sirius A is relatively close to us, you should know that it is substantially hotter and more luminous than our own Sun, shining with a distinct white-blue light. This coloration is a direct indicator of a star's surface temperature. Hotter stars radiate energy at shorter, bluer wavelengths, while cooler stars emit light at longer, redder wavelengths. The surface temperature of stars is measured using the Kelvin scale, where 0 corresponds to absolute zero, the theoretical point at which all thermal motion of particles ceases. At this temperature of 0 Kelvin, or negative 273.15 degrees Celsius, an ideal crystal would reach its minimum state of entropy and internal energy. In essence, it is the temperature where molecules and atoms stop vibrating, and thermal energy is effectively gone. While reaching absolute zero is physically impossible, scientists in laboratory settings can get remarkably close, enabling them to explore quantum phenomena and the properties of matter at extreme lows. You might imagine that most of outer space, being a near-perfect vacuum with highly dispersed matter, exists at this temperature. This environment, known as the interstellar medium, is indeed incredibly cold, but it's crucial to understand that temperatures across space are not uniform and fluctuate based on proximity to heat sources like stars. In the vast emptiness of interstellar space, far from any stellar influence, the ambient temperature hovers around 2.7 Kelvin. This residual warmth is actually the cosmic microwave background, which is the faint afterglow of radiation from the very beginning of the universe, the Big Bang. However, as you get closer to stars or other heat-emitting celestial bodies, their thermal radiation causes the surrounding temperature to rise significantly. The relationship between light's color, its wavelength, and temperature is dictated by fundamental physical laws like blackbody radiation. You can observe these principles in everyday phenomena. A simple candle flame, for instance, glows with a reddish-orange hue because it burns at around 1,500 Kelvin, a temperature corresponding to the longer wavelengths in the visible spectrum. This spectrum ranges from red, which has the longest waves, to violet, which has the shortest. The same principle applies directly to the stars you see in the night sky. The color of a star is a reliable guide to its surface temperature. Exceptionally hot stars with very high surface temperatures radiate light that is shifted towards the blue or ultraviolet end of the spectrum, signifying shorter wavelengths. Conversely, cooler stars emit a reddish light, indicating longer wavelengths. A star of intermediate temperature, like our Sun, emits a bright yellow light because the temperature of its photosphere, its visible surface, falls between that of hot blue stars and cooler red ones. To give you precise figures, the Sun's surface temperature is about 5,778 Kelvin. Hot blue stars can range from 20,000 to 50,000 Kelvin, whereas relatively cool red stars have surface temperatures between 2,000 and 5,000 Kelvin. By simply observing a star's color, you can see how astronomers are able to deduce how hot its surface is, which provides deep insights into its physical characteristics and its current stage of evolution. Circling back to Sirius A, its surface temperature is approximately 9,900 Kelvin, making it considerably hotter than our Sun. Structurally, it is a fairly typical star, with a core where nuclear fusion converts hydrogen into helium, releasing immense energy. These reactions are analogous to those inside the Sun, but proceed at a much greater intensity, because Sirius A is more massive. The elemental makeup of Sirius A is also quite similar to the Sun's, consisting mostly of hydrogen and helium, but it also contains heavier elements like oxygen, carbon, and nitrogen. In astronomical terms, you should know that any chemical element other than hydrogen and helium is referred to as a metal. This convention exists because hydrogen and helium were the primary elements formed at the dawn of the universe. All the other elements that make up our world were forged later, inside the cores of stars, through the process of nuclear fusion under extreme heat and pressure. Lighter elements combine to create heavier ones, which are then scattered into space when massive stars explode as supernovae. This material goes on to form new stars, planets, and everything you see around you, including Earth itself. The term used in astronomy to describe this concentration of heavier elements in a star is its metallicity. This particular parameter provides astronomers with vital clues about an astronomical object's age, origins, and history, making it a surprisingly crucial tool for investigating the cosmos. You can think of Sirius A as a more powerful counterpart to our own Sun. It's larger, hotter, and radiates more light. In essence, it represents a high-performance version of our star, a sort of sun maxed out, which establishes it as an object of immense importance in astronomical study. Its fascinating companion, Sirius B, is a white dwarf, which is a compact yet extraordinarily dense stellar remnant that presents a stark contrast to our Sun. You have to picture an object containing nearly the entire mass of the Sun, compressed into a volume no larger than the Earth. The surface of Sirius B burns at an extreme temperature, reaching approximately 25,000 kelvins. If you were able to get close to Sirius B, you would find that, for all its smallness, it is intensely hot and shines with a white light, although its luminosity is far less than that of its neighbor, Sirius A, or our Sun. The glow from this white dwarf is predominantly in the ultraviolet part of the spectrum, which accounts for its white appearance. Having exhausted the fuel in its core, Sirius B has finished the main sequence of its evolution and is now in the white dwarf phase, a state in which it cools down at an exceptionally slow rate. When you compare it with the Sun, Sirius B resembles a wise elder among the stars. It has already journeyed through numerous life stages and is now settling into a quiet period of gradual fading. All of its dramatic nuclear fusion processes are in its past, whereas our Sun is currently in the vibrant middle of its life. Yet, despite its present condition, Sirius B was once a significantly more massive star than it is today. Stars with greater mass, like the former Sirius B, progress through their life cycles much more rapidly, because they burn through their reserves of nuclear fuel at a far greater speed than smaller stars like the Sun. This allowed Sirius B to transition into a white dwarf after a comparatively brief but spectacular existence. Our Sun, on the other hand, is still in its primary life phase, after about 4.5 billion years, with an estimated 5 billion more years to go. The architecture of the Sirius system is quite distinct from our own solar system. Both Sirius A and Sirius B are locked in orbit around a mutual center of mass, performing a dynamic and magnificent cosmic waltz. You might visualize this as a pair of performers, where Sirius A is the large, powerful lead, and Sirius B is the small but exceptionally nimble and quick partner. They circle a common point without ever making contact, preserving a flawless balance and harmony in their motion. This celestial ballet is reminiscent of planets circling the Sun, but there's a key distinction. In our solar system, the Sun remains relatively fixed at the center, while the planets orbit it. In the Sirius system, both stars are active participants in the orbital motion. The disparity in their masses makes this dynamic rotation of Sirius A and B particularly unique, causing Sirius B to follow a longer and more eccentric path than its heavier companion. This intricate performance continues to fascinate astronomers with its singular dynamics and structure. By examining the light from Sirius through spectroscopy, we can uncover the deeper secrets of this incredible stellar system. In spectroscopy, we primarily work with two kinds of spectral lines: absorption and emission lines. Absorption lines are created when light from a star passes through a cooler gas or atmosphere. Atoms within this gas capture photons at specific wavelengths, which correspond to electrons jumping to higher energy levels. This process leaves dark lines in the star's continuous spectrum, showing where the light was absorbed. Emission lines, conversely, are formed by gases that are heated to the point of glowing. In this scenario, the atoms within the gas release photons as their electrons drop from higher energy states back to lower ones. These photons manifest as bright lines in a spectrogram, revealing the exact wavelengths of light that were emitted. Spectroscopy, therefore, enables us to interpret the light signatures of atoms, providing insights into the physical and chemical makeup of celestial objects. If you were to contrast Sirius with the Sun, you could say that each star possesses a distinct spectral fingerprint. It is as if the Sun is attired in a brilliant yellow, showcasing its warmth and bright energy, while Sirius is cloaked in a radiant blue-white, a reflection of its higher temperature and energetic state. Through spectroscopy, we can decipher these light signatures to determine the elemental composition of stellar atmospheres and understand the fundamental physical processes at play within them. The spectroscopic techniques used to analyze Sirius are fundamentally similar to those we use for the Sun, but they are specially calibrated for a star with vastly different properties. Spectroscopic observation of Sirius unveils astonishing details about its chemical makeup, atmosphere, and magnetic fields. This helps astronomers gain a clearer understanding of how this star is built and operates in comparison to our own home star. The gravitational pull of Sirius B on its system is like a subtle force that orchestrates the stellar dance. In our solar system, the Sun serves as the primary director. Its immense mass and gravity hold the planets in their orbits, much as a powerful magnet holds on to metal. Sirius B, despite its modest size, wields an exceptionally strong gravitational field because of its incredible density. This white dwarf influences the motion of Sirius A and any other bodies within the system, shaping their paths through space, much like a small but potent magnet compared to the Sun's larger, brighter one. Sirius B projects a gravitational force that shapes the orbits of nearby objects. Despite being substantially smaller than our Sun, its gravitational pull is a decisive factor in the system's overall dynamics, proving that even compact celestial bodies can have a profound effect on their cosmic neighborhood. The hunt for exoplanets there is ongoing, as they have yet to be found, waiting for their moment of discovery. This pursuit feels like a grand treasure map, with astronomers using their most sophisticated technologies to scan the Sirius system for new worlds. Here in our own solar system, the planets are vibrant and accessible targets for study, each one distinct and remarkable. I remember as a boy being captivated by a book about our solar system from the 1950s. It was filled with imaginative descriptions of Venusian jungles and Martian canals, written, of course, before the dawn of space exploration. I admit, I still feel a little let down by those wonderfully optimistic authors. The reality we discovered was a hellishly hot Venus, a frigid desert on Mars, and the gas giant Jupiter, each telling a unique chapter in our system's history. Searching for exoplanets around Sirius presents a much greater challenge, largely because of the vast distance and the overwhelming brightness of Sirius A. Its intense glare acts like a celestial spotlight, obscuring our view and making it incredibly difficult to spot any potential planets orbiting it, Sirius B, or the pair. Imagine trying to discern tiny, faint specks of light right next to a blindingly bright lantern. Nevertheless, the research presses on, employing a variety of methods in the hope of revealing these undiscovered worlds. Every new piece of data brings us closer to understanding the universe's structure and the astonishingly diverse worlds it might conceal. The Sirius star system itself, much like a legendary figure from an epic tale, has passed through numerous phases in its existence. Its evolutionary journey is a narrative of transformation and resilience within the ever-shifting and often unforgiving theater of the cosmos. So, if the writers from before the space age could dream, let's allow ourselves the same freedom. In the Sirius system, we could speculate about an incredible variety of potential planets. There might be gas giants akin to Jupiter or Saturn, complete with immense atmospheres and spectacular ring systems. You could also envision water worlds, featuring vast global oceans and atmospheres thick with water vapor, methane, and ammonia. We might even find Earth-like planets, offering the right conditions for life, boasting moderate climates and liquid water on their surfaces. Closer to Sirius, scorching volcanic worlds could exist, while frozen, unforgiving ice planets might occupy the system's distant orbits. Beyond these, we could discover truly exotic planets that would defy our expectations, perhaps harboring new forms of life and presenting entirely new realms for exploration. Any life in the Sirius system would have to be uniquely adapted to its environment. For instance, on a planet orbiting Sirius A, The different light spectrum might cause plants to evolve blue or purple pigments to photosynthesize more effectively under the star's intense glow. The sky's color would also vary based on atmospheric composition. While a nitrogen-oxygen mix like Earth's would produce a blue sky, other gases could paint it in entirely different shades. The possibility of life, from simple microbes to complex organisms, implies the development of unique adaptations and even technological solutions shaped by their environment. When we formulate hypotheses about alien life, we have to acknowledge that our ideas are rooted in terrestrial biology, and the actual forms life takes elsewhere could be profoundly different and far more amazing than we can imagine. These thought experiments fuel our excitement for future discoveries within the Sirius system. The system is still relatively young, and its turbulent history adds another layer of intrigue to its study. It's plausible that violent events, like massive solar flares or asteroid impacts, have forged distinctive conditions on its potential planets. Being so bright and hot, Sirius A undoubtedly exerts a powerful influence, creating extreme environments characterized by high temperatures, intense ultraviolet radiation, and potent solar winds that would dramatically shape any planetary atmospheres and surfaces. As the system continues to evolve, conditions might become more stable, creating new opportunities for life to emerge and adapt. Looking back into the distant past, about 230 million years ago, long before the dinosaurs, the Sirius system would have appeared even more brilliant and powerful in the night sky. Back then, Sirius B was not the white dwarf we see today, but was likely a star far more massive and luminous than our own Sun. The fact that it became a white dwarf faster than Sirius A reveals a crucial detail. Sirius B began as the more massive of the two stars. Stars with greater mass burn through their fuel much more rapidly, accelerating their journey through the stages of stellar evolution. In its distant past, Sirius B may have been a far more luminous star than it is today. After consuming most of its fuel, it expanded into a red giant and subsequently collapsed into a white dwarf, shedding its outer layers to leave only its hot, dense core. Sirius A, on the other hand, is still in its main sequence phase, a period of stellar life where it shines brightly because it was less massive than Sirius B and is burning through its nuclear fuel more gradually. As a result, in Earth's ancient skies, the Sirius system would have appeared as a spectacular binary star. Sirius A, which is already one of the brightest stars from our perspective, would have been even larger and more brilliant in its youth. Together, they would have presented an incredibly bright and dynamic celestial show for the primeval Earth, potentially serving as a major beacon for early life forms, and possibly influencing their natural cycles in a way similar to how our Sun and Moon affect life today. From our current viewpoint, Sirius A and Sirius B are so close to one another that they appear to be a single, exceptionally bright star. This fusion of two stellar images into one brilliant point in the sky could have made Sirius an even more prominent and enigmatic feature, likely drawing the attention of ancient life. While it is true that Sirius is moving toward our solar system at a speed of approximately 7.6 kilometers per second, the chances of a collision are practically zero, given the immense scales of space. It is also crucial to remember that the movements of stars in the galaxy are governed by gravity and other physical laws, which allows for their trajectories to be forecast with considerable accuracy, and provides confidence that a collision between Sirius and our solar system is not going to happen. But can we anticipate any surprises from the Sirius system? The answer is yes, because Sirius B, the closest white dwarf to us, holds a key role in a potential future event known as a nova explosion. The scenario could be triggered when Sirius A exhausts its fuel, swells into a red giant, and starts transferring its mass to Sirius B. This accumulation of matter could then ignite thermonuclear reactions on the white dwarf's surface, causing it to erupt in an explosion we would see as a nova. Such an event would have a variety of consequences for Earth, including the emission of intense ultraviolet, X-ray, and gamma radiation that could harm our ozone layer and impact various forms of life. Spacecraft, including satellites in Earth's orbit, would also be at risk from the heightened radiation levels. The light from this nova could become so intense that it would transform the night sky, and might even be visible during the day. However, despite the relative proximity of Sirius B, the significant distance to our solar system acts as a safety buffer, limiting the potential risks and shielding Earth from most of the explosion's negative effects. It is important to distinguish between novae and supernovae, as they are two different astronomical phenomena with unique characteristics. A nova results from an explosion on the surface of a white dwarf, which is fueled by material from a companion star. The white dwarf survives and can experience many such events. By contrast, a supernova represents the final, cataclysmic stage of a star's life, during which the star is completely obliterated. A supernova explosion utterly destroys a star, leaving behind a neutron star or a black hole, and releases an incredible amount of energy that can temporarily outshine its entire host galaxy. Consequently, if a supernova were to detonate where Sirius is now, the effects on Earth would be extremely dire. A powerful pulse of radiation would likely destroy the ozone layer, leading to catastrophic climate changes and mass extinctions from the increase in ultraviolet radiation. Furthermore, streams of high-energy cosmic rays from the blast could trigger widespread radiation and electromagnetic anomalies, disrupting both our technology and biological systems. The explosion could even alter the orbits of planets and other celestial objects in the solar system due to its powerful dynamic and gravitational shock waves. A supernova would also enrich our solar system with new heavy elements, and visually, the sky on Earth would become so bright that night might appear like day, disrupting nocturnal ecosystems. Even neutrinos, elementary particles that typically pass through matter with little interaction, could become a hazard in the event of a nearby supernova. The sheer quantity of emitted neutrinos could have a tangible impact even at vast distances, potentially interacting with Earth's atmosphere, geosphere, and biosphere. For life on our planet, this could cause effects such as increased radioactivity and mutations in organisms. Although for such a truly catastrophic outcome, the supernova would need to be relatively close. For a supernova to severely affect our biosphere, it's generally thought the star would have to explode within a radius of about 30 light-years. Sirius, as you know, is positioned more than 3 times that distance from us. While Earth's solid and liquid layers might absorb some particles and lessen the impact on its far side, devastating effects would still be conceivable. Fortunately, such cosmic events are exceedingly rare, and our planet faces a very low probability of being affected, as there are no supernova candidates in our immediate celestial neighborhood. While the search for planets orbiting Sirius came up empty, the effort demonstrated that the technologies and methods employed could be highly effective for future explorations and characterizations of objects around nearby white dwarfs. Scientists often encounter technical hurdles when hunting for planets in binary systems, particularly when using the radial velocity method, which has led to an incomplete catalog of exoplanets. Although researchers have determined that the overall occurrence of planets is similar for both single and binary star systems, they also theorize that planet frequency might be lower in systems where the stellar components are very close together. The Sirius system presents a fascinating case as a binary star with powerful magnetic fields that exert influence over the surrounding space and potentially affect other cosmic bodies in its vicinity. The magnetic field of Sirius A is produced by convective motion within its inner layers, which generates a dynamo effect. In contrast, Sirius B, being a white dwarf, possesses magnetic fields that are substantially stronger than those of typical stars, a result of its immense density and swift rotation. A white dwarf's magnetic field can attain extraordinarily high values, making Sirius B a subject of great interest for astrophysicists. These magnetic fields within the Sirius system can shape a variety of cosmic phenomena, including particle emissions, the solar wind, and how the stars interact with the interstellar medium around them. They are also critically important for studying diverse areas of astrophysics, such as the processes stars undergo throughout their evolution, the mechanisms that generate magnetic fields, and the resulting impact on their cosmic environment. As the white dwarf companion to Sirius A, Sirius B stands out as a truly remarkable object in the astronomical world, with its unique atmospheric and internal properties being a primary focus of scientific investigation. The atmosphere of Sirius B is composed mainly of hydrogen and helium, along with trace amounts of heavier elements. The intense surface gravity of the white dwarf causes these heavier elements to sink, which leaves an atmosphere dominated by the two lightest elements. White dwarfs are the evolutionary endpoints of stars that have depleted their nuclear fuel. Since there are no ongoing nuclear reactions in their cores, they no longer produce the powerful radiation stream that once created the outward pressure needed to counteract gravitational collapse, leading to even stronger gravitational forces on the surface. The material composing a white dwarf is incredibly dense, a consequence of the extreme conditions under which it exists. Having shrunk dramatically under its own gravity, the matter is so compressed that a single teaspoon of it would weigh approximately 1 ton on Earth. This is, of course, an estimation, as the exact weight would depend on specific factors like the white dwarf's composition, temperature, and internal pressure. Still, this comparison powerfully illustrates the phenomenal compression and density of matter within a white dwarf. The atmospheric temperature of the white dwarf Sirius B is extremely high, reaching around 25,000 kelvins, which is hot enough to ionize the matter and form a plasma. Exploring the internal structure of Sirius B, it's important to understand that its core is a hot, dense mass primarily made of carbon and oxygen. This core is enveloped by a shell of what is known as degenerate matter, a state where particles, typically electrons or neutrons, are forced into their lowest possible quantum states due to exceptionally high density and pressure. To better understand this concept, you can look at the examples of white dwarfs and neutron stars. In white dwarfs, gravitational collapse is halted by the pressure of a degenerate electron gas. The electrons are compressed so tightly that they occupy all available quantum states, creating a pressure that resists further compression. Neutron stars, conversely, are far more massive objects, composed mostly of degenerate neutrons. Following the collapse of a massive star, protons and electrons merge into neutrons, which then generate the immense pressure that counteracts gravity. Degenerate matter possesses very unusual properties and is not found under normal conditions on our planet. This exotic state of matter is a defining feature of cosmic objects with extreme density and pressure, like white dwarfs and neutron stars. Ultimately, the precise structure and atmospheric details of Sirius B continue to pose many questions for scientists. The distinct properties of white dwarfs, including their immense density, high temperature, and powerful gravity, render them uniquely complex and challenging objects to study anywhere in the universe. The formation of two stars from a single cloud of molecular gas, like hydrogen, often begins when vast interstellar clouds of gas and dust accumulate enough mass to create several stars, sometimes enriched with heavy elements from supernova explosions of prior stellar generations. The collapse of such a cloud can be initiated by various triggers, such as shock waves from supernovae, collisions between clouds, or the gravitational pull of massive nearby objects. In certain situations, the cloud can start to contract under its own gravity once it achieves a critical mass and density. As this contraction proceeds, the cloud can break into fragments, setting off the processes that lead to the formation of protostars, which involve significant heating and the ignition of nuclear reactions. When multiple protostars form within the same cloud, they can become gravitationally linked, giving rise to binary or multiple star systems. These protostars then continue their development until they stabilize and enter the main sequence, becoming fully fledged stars. This entire process demonstrates how star formation is deeply connected to the life cycles of previous stellar generations, their explosive deaths, and the subsequent enrichment of the interstellar medium with heavy elements. While centrifugal forces do influence the dynamics of a rotating molecular cloud, the final distribution of elements within it is shaped by a complex interplay of factors including temperature, density, and internal turbulence. Heavy elements and metals, seeded into a cosmic cloud by the supernova explosions of prior stellar generations, might be dispersed evenly or become clustered in specific regions through processes like particle condensation and coagulation. As a stellar system, complete with its star and planets, takes shape, the material within the disk encircling the young star condenses into protoplanetary zones, which can eventually form larger bodies. You might think we have a solid grasp on how planets emerge from cosmic dust, but, to be honest, the formation of the cosmic dust itself is not well understood. In fact, pinpointing the origins of this dust remains one of the great puzzles in astrophysics. Broadly speaking, we know dust is composed of tiny solid particles adrift in space, with sizes that can vary from just a handful of molecules to several millimeters. These cosmic dust particles are fundamental to the creation of planets and stars, as larger celestial objects are built up through aggregation and accretion. Dust can originate from a variety of cosmic settings, including stars like red giants, which frequently shed material via stellar winds that cool to form solid particles. Likewise, immense supernova explosions expel huge quantities of matter, including heavy elements that can coalesce into minute grains of dust. Within the protoplanetary disks of young star systems, the merging and compression of matter also play a significant role in creating these dust grains. However, despite our general knowledge of these potential sources, many specifics of the formation mechanisms are still unknown. For instance, the processes involved are incredibly complex and multifaceted on a cosmic scale, and we lack a full understanding of how individual atoms and molecules assemble into solid particles. We also don't fully comprehend how these particles engage with their environment, or which factors ultimately dictate their size, makeup, and distribution throughout space. The investigation into cosmic dust requires analyzing information from space probes, studying the interstellar medium through observation, and performing laboratory experiments that replicate cosmic conditions. Progress in these fields will undoubtedly give scientists a clearer picture of the processes that drive the formation of cosmic dust. Even in its most concentrated areas, such as molecular clouds, the interstellar medium is extraordinarily sparse compared to the conditions you experience on Earth. Still, encounters between atoms and molecules can cause them to merge, initiating the formation of dust particles. This process can be outlined in a few key stages. Gas atoms and molecules in interstellar space can attach themselves to existing solid particles, while weak attractions known as van der Waals forces can draw neutral atoms and molecules close enough to form tentative bonds. In certain cosmic environments, chemical elements can react, producing more complex molecules. For example, carbon-rich areas can give rise to intricate organic molecules that act as a sticky foundation for further material to accumulate. Dust particles can also build up a static charge, which attracts other charged particles and helps them grow. In the colder reaches of space, cores of dust can acquire icy mantles, which adds to their overall size. When particles collide, they can stick together, provided their relative velocity is low enough that their kinetic energy doesn't overcome the binding forces. While each of these mechanisms operates on a timescale that is exceptionally slow by human standards, over astronomical epochs, they are more than capable of generating substantial quantities of cosmic dust. In denser regions, like the protoplanetary disks around young stars, these processes unfold much more rapidly. Although centrifugal forces certainly affect the dynamics of clouds and protoplanetary disks, the greater abundance of iron in Sirius A, compared to our Sun, can be attributed to several factors tied to stellar evolution and their differing histories. The quantity of iron and other heavy elements in a star is determined by the chemical makeup of the molecular cloud from which it formed. Sirius A, being a relatively young star of spectral class A, likely originated from a cloud that was heavily enriched with material from the supernovae of previous stars. Stars of this type often exhibit a high metallicity, a term astronomers use for any element heavier than helium. Supernova events are responsible for creating and scattering heavy elements like iron into the interstellar medium, which then get incorporated into subsequent generations of stars. Therefore, the elevated iron content in Sirius A is a logical consequence of its youth and the enriched conditions of its stellar nursery. During the birth of a protostar, a fundamental conflict arises between gravity, which works to collapse the gas and dust cloud, and the radiation pressure from internal nuclear reactions, which pushes outward. This process begins with gravity's dominance, causing the cloud to shrink while increasing the temperature and density at its core. Once the conditions are extreme enough, nuclear fusion ignites, chiefly the conversion of hydrogen to helium, unleashing vast energy that creates an outward radiation pressure. Eventually, the star reaches a point of equilibrium where the inward pull of gravity is perfectly counteracted by the outward force of radiation pressure. At this moment of balance, the star becomes stable and enters what is known as the main sequence stage of its life. A star can remain in a stable phase for a considerable duration, powered by the nuclear reactions occurring deep within its core. As its hydrogen fuel is gradually consumed, the fusion of more massive elements commences, which in turn alters the star's internal structure and behavior. Throughout the majority of its existence, radiation pressure is essential. not only for balancing the inward pull of gravity, but also for sustaining these critical nuclear processes. However, some low-mass protostars go through unstable phases, where nuclear fusion ignites briefly, only to be extinguished by insufficient temperature or pressure. When this occurs, the burst of energy can blow away a portion of the protostar's material, halting any further gravitational collapse. This means that the mere ignition of nuclear reactions does not always guarantee the creation of a stable, long-lived star. While you might think we have a solid grasp on how stars are born, my conversations with top researchers in astrophysics revealed just how much remains a mystery. We understand the basic framework. Stars emerge from vast molecular clouds as gas and dust collapse under their own gravity. Yet this simple picture hides profound questions, such as what specific event, be it powerful stellar winds or a supernova shockwave, actually triggers this initial collapse. Another major puzzle involves angular momentum. As a cloud contracts, it spins faster, and this powerful centrifugal force must somehow be reduced for a star to form. The leading theory suggests that magnetic fields, combined with the flow of matter in the disk around the protostar, are instrumental in carrying this excess momentum away, though the exact mechanics are still being actively debated. The moment thermonuclear reactions ignite presents a critical crossroads. The resulting outward pressure can either trigger the formation of more stars in the surrounding gas, or disperse that material entirely, effectively ending the star-birthing process. We also observe a universal pattern in stellar masses, known as the initial mass function. But the physical laws that dictate this specific distribution remain one of astrophysics' great, unsolved problems. Researchers are also exploring how the evolving chemical makeup of interstellar clouds over cosmic time influences star formation. To tackle these complex questions, scientists use everything from multi-wavelength observations to sophisticated computer modeling. Despite remarkable progress, each new answer we find often uncovers an even deeper layer of questions for you to consider. Now, let's consider the binary system of Sirius A and B, whose orbits have undoubtedly changed over time. In the distant past, before Sirius B became a white dwarf, it was a much more massive red giant. In that era, the system would have been more compact, with the two stars orbiting each other more quickly and in a more circular path due to the stronger gravitational bond between them. The transformation of Sirius B into a white dwarf involved shedding a substantial amount of its mass, which dramatically altered the system's dynamics. This mass loss weakened the gravity holding the pair together, likely causing their orbit to become more elongated and significantly increasing the time it takes for them to complete one revolution. During its closest orbital pass to Sirius A, the gravitational forces on Sirius B intensify, creating tidal effects that can deform and heat both stars. It's plausible that when Sirius B was an enormous red giant, its outer layers were siphoned off by its companion, profoundly influencing their shared evolution. There's even a chance that other objects once existed in the system, but were later ejected by gravitational instabilities. Unraveling the complete history of this dynamic duo requires detailed analysis and simulation. Confirming whether any long-lost objects ever existed is challenging without direct evidence, but the field of astrometry is crucial in this effort. It provides the precise measurements of the system's distance from Earth and other key parameters needed to model its complex past and predict its future. Astrometry is a crucial field within astronomy, dedicated to mapping the positions of stars and other celestial bodies while also calculating their distances and motions. To determine the distance to a star like Sirius, astronomers employ a variety of techniques, with the parallax method being one of the most fundamental. This approach involves charting the apparent shift in a star's position against a background of more distant objects as the Earth completes its orbit around the Sun. By measuring this angular change and knowing the diameter of Earth's orbit, the star's distance can be calculated through simple trigonometry. Modern astrometry has been revolutionized by advanced instruments such as the Gaia Space Telescope, which measures stellar parallax with extraordinary precision. It is through these sophisticated technologies that the distance to Sirius has been confidently estimated at approximately 8.6 light-years. Such accurate measurements are invaluable, as they enable astronomers to derive the fundamental properties of Sirius, including its true luminosity, mass, and size, and to conduct detailed studies of its binary system, exploring the complex interactions between its two component stars and their impact on the surrounding space. Measuring the vast distances to stars represents one of astronomy's most significant challenges, particularly for objects far beyond our galactic neighborhood. For the closest stars, the parallax method remains effective, leveraging the apparent motion caused by Earth's orbit. However, the usefulness of this technique rapidly declines for stars more than a few hundred light-years away, forcing scientists to turn to other methods for probing deeper into the cosmos. To gauge the distances to more remote objects, astronomers utilize what are known as standard candles, celestial bodies like Cepheid variables or Type 1a supernovae that have a known intrinsic brightness. By comparing an object's absolute luminosity to how bright it appears from Earth, its distance can be inferred. The primary weakness of this method, however, is that any miscalculation of the standard candle's true brightness will result in substantial errors in the final distance estimate. For the most remote galaxies, astronomers rely on measuring redshift, a phenomenon tied to the expansion of the universe that causes distant objects to move away from us. This technique is also dependent on precise data, as an accurate distance calculation requires an exact understanding of the universe's expansion rate. The various assumptions and adjustments inherent in these methods can lead to significant inaccuracies in distance measurements, which carry profound implications for our cosmological models. These measurement uncertainties can distort our entire perception of the cosmos, leading to flawed estimations of the universe's scale, its age, and the physical processes that govern galaxies. In response, scientists are perpetually refining observational techniques, from leveraging advanced space telescopes to developing new methods like laser interferometry. For distant objects measured using standard candles or redshift, these potential inaccuracies can be dramatic, with errors sometimes reaching as high as 50% or more. This level of uncertainty arises because the entire calculation hinges on the reliability of the standard candle. If its absolute brightness is even slightly misjudged, the error is amplified in the distance result. Such discrepancies have a ripple effect, undermining our understanding of stellar and galactic evolution, and potentially leading to false conclusions about the mass, luminosity, and life stage of stars. Consequently, our foundational models of galactic structure and the cosmos itself may be built on flawed data, which provides a constant motivation to enhance our technology and discover more accurate measurement techniques. In the cosmos, Star systems containing two or more stars are far more prevalent than solitary stars like our Sun. The formation of these binary and multiple systems is thought to be a natural outcome of the dynamics within collapsing clouds of gas and dust. As these nebulae contract, instabilities such as rotation, turbulence, and centrifugal forces can cause the cloud to fragment into multiple dense cores. Each of these cores can then evolve into a protostar, leading to the birth of a multi-star system. While the dynamic processes in stellar nurseries often favor the formation of multiple stars, the emergence of a single star is still a frequent occurrence. A lone star can form when a gas and dust cloud has a sufficiently dense central core to initiate gravitational collapse on its own. This outcome is more likely if the cloud is relatively stable, with minimal turbulence or external disruption, and if it rotates slowly, which lessens the fragmenting influence of centrifugal forces. Although nearby stars or radiation pressure can alter this process, the conditions required to form a single star are not considered exceptionally rare. An important characteristic of the Sirius system is that the orbit of its smaller companion, Sirius B, around the primary star, Sirius A, is not aligned with the plane of Earth's own orbit around the Sun. This means the orbital path of the two stars is tilted relative to our perspective here on Earth, a critical detail for astronomers who model and observe this fascinating binary pair. In a dual star system, the term ecliptic generally signifies the orbital plane in which the two stars circle their shared center of mass. This plane encompasses both stars and their gravitational balance point, and it is within this plane that their orbits unfold. While the word ecliptic can be applied here, especially if one star resembles our Sun, astronomers often prefer the term orbital plane to prevent any mix-up with our own solar system's ecliptic, and to be clear that the subject is the motion within a binary star system. The orbital plane of Sirius B undergoes precession, a gradual shift in the orientation of a rotating object's axis caused by external gravitational pulls. You might be familiar with this phenomenon from Earth's own axial precession, where our planet's rotational axis slowly wobbles, causing the poles to trace circles against the backdrop of space. This effect is responsible for long-term changes in the night sky, altering the positions of constellations and equinoxes over millennia. Precession can also describe shifts in the orientation of one body's orbit around another, a process driven by the gravitational influence of other objects within the system. You can see this effect in the orbits of planets around the Sun, and it is also at play in binary star systems like Sirius. Consequently, when you observe the Sirius system from Earth, you are not seeing a perfect circle, but rather a projection of Sirius B's inclined orbit onto the celestial sphere. A compelling body of evidence from astronomical studies indicates that Sirius A and Sirius B were formed together, rather than one capturing the other. Their nearly identical direction and speed of travel through the cosmos strongly suggest a common origin. When two stars move in such a synchronized manner, it is almost always a sign that they were born from the same vast molecular cloud. Furthermore, spectral analysis, which reveals a star's chemical makeup by studying its light, shows that Sirius A and B have remarkably similar compositions, pointing to their formation from the same primordial material. The stable nature of their orbits also reinforces the idea of a shared birth. A gravitational capture would likely result in chaotic, unstable elliptical paths, not the predictable system you see today. It's true that Sirius B follows an elliptical path around Sirius A, but this does not contradict the joint formation theory. In fact, Perfectly circular orbits are quite uncommon in binary systems. The initial conditions within the swirling disk of gas and dust from which they emerged could have easily introduced some eccentricity into their paths. Over billions of years, these orbits tend to stabilize through gravitational interactions. Keep in mind that Sirius B, now a white dwarf, is at the end of its life cycle and was once a much more massive star. The system's long and dynamic history, involving significant changes in the mass and size of both stars, has shaped the orbit you now observe. Therefore, its current elliptical path is perfectly consistent with the astronomical models that overwhelmingly favor a scenario of co-formation. This conclusion is further supported by age estimates for both stars, which align closely, and by computer simulations demonstrating that a random gravitational capture is statistically improbable and would have caused major dynamic disruptions. The long-term stability of their orbits is another key piece of evidence, showing the system has been free from the kind of external disturbances associated with a capture event. Detecting planets in a binary system such as Sirius presents a unique set of challenges. The complex gravitational environment created by two stars can make it exceedingly difficult to find planets using standard techniques like the radial velocity or transit methods. Moreover, if the system's orbital plane is not aligned with your line of sight from Earth, discovering a planet as it passes in front of its star becomes highly improbable, or even impossible. The sheer brightness of Sirius, one of the most luminous stars in our sky, creates a significant observational hurdle. The overwhelming amount of light it produces can easily mask the subtle dimming caused by a transiting planet. Even if a planet were to cross the disk of one star, the light from the other star in the system could easily wash out the signal, making detection incredibly difficult. You'll find that the existence of two stars introduces a far more complex and potentially unstable dynamic for any orbiting planets, affecting both their orbital paths and the very likelihood of their detection. The dual light sources also make spectroscopic analysis, which we use to look for evidence of planets or their atmospheres, a much more intricate task. Consequently, discovering planets in binary star systems, such as Sirius, demands a more meticulous and thorough examination of the data, employing sophisticated methods of observation and analysis. Now, you might ask how two stars in a binary system, born at roughly the same time, can find themselves at completely different stages of their evolution. To answer this, I must point out several crucial factors, the most important of which is mass. Stars with greater mass burn through their nuclear fuel at a much faster rate, causing them to progress through their life cycles far more quickly. A star's composition can also steer its evolutionary course, as varying amounts of heavy elements can alter the temperature and pressure within its core and influence internal processes like convection. Within binary systems, you see, the stars can actually interact, exchanging mass and energy in a way that profoundly reshapes their individual life stories. In the Sirius system, for example, Sirius B is a white dwarf with a smaller current mass than its companion Sirius A. Despite this, it has already lived through its main sequence and red giant phases precisely because, in the distant past, it was the more massive of the pair. Sirius B accelerated its own evolution by shedding a large part of its mass, either into the surrounding space or directly onto Sirius A, before settling into its current state as a white dwarf. Meanwhile, Sirius A, which is now the more massive star, remains on the main sequence and has yet to start its own journey toward the later stages of stellar evolution. These two stars, separated by an average distance of 20 astronomical units, exert a mutual influence on each other, and on any potential planetary system. The tidal forces between them can deform and heat the stars internally, impacting their evolution. The complex and rapidly shifting gravitational fields generated by their orbits also make the existence of stable planetary orbits less probable. Planets within such a system would be subjected to immense tidal forces, potentially leading to intense geological activity, while also experiencing dramatic climate shifts from the variable radiation of two suns. The processes of planet formation itself are complicated by a dual star environment, and any planets that do form would likely face more frequent orbital disturbances over time. I believe it's safe to conclude that the conditions in the Sirius system make stable, long-term planetary development far less likely than what you would find around a single star. As I mentioned, Sirius B was once more massive than Sirius A, which is explained by the fact that more massive stars burn through their evolutionary stages faster due to more intense nuclear reactions. Over eons, Sirius B cast off a substantial portion of its outer envelope as it transitioned through its red giant phase. This material, composed mostly of hydrogen and helium, was likely expelled into space as a powerful stellar wind or during the formation of a planetary nebula. It is also quite possible that a portion of this ejected matter was captured by Sirius A in a process known as accretion, which would have increased its mass and potentially altered its own evolutionary path. This doesn't mean planets are impossible, however. I find it entirely plausible that in binary systems like Sirius, planets could form and maintain stable orbits at much greater distances, circling the central pair. These are what we call circumbinary planets, and their orbital stability depends on a number of factors. For instance, planets in more remote orbits are less affected by the powerful gravitational disruptions of the two stars. The masses of the stars and the size of their orbits also play a critical role, as greater mass and closer proximity between the stars can generate more instability for any surrounding bodies. Therefore, while you can see that the formation and persistence of planetary orbits around binary stars is a complex challenge, it is certainly not impossible, especially for planets orbiting far from the stellar pair. Detecting these circumbinary worlds can be achieved through several techniques, with the transit method being a primary one. This approach involves searching for tiny periodic dips in the brightness of the stars. These mini-eclipses, or transits, occur when a planet passes in front of one or both stars from our point of view, momentarily blocking a fraction of their light. Next is the radial velocity method, also known as the Doppler method. This technique relies on measuring shifts in a star's spectrum that are produced by the Doppler effect, which in turn is caused by the gravitational tug of an orbiting planet. In the case of circumbinary planets, however, the presence of multiple stars complicates these measurements, making analysis more challenging. A third approach is gravitational microlensing, which involves searching for brief flare-ups in a star's brightness caused by the lensing effect of a planet and its host star passing in front of a more distant one. Another technique, direct imaging, involves capturing actual images of planets with powerful telescopes, a feat that demands highly sensitive instruments and is typically used for detecting planets far from their stars. Then there is astrometry, which meticulously measures the precise position of a star in the sky, tracking the subtle changes brought about by a planet's gravitational pull to confirm its presence and map its orbit. Finally, scientists can study transit timing variations, where slight alterations in the predictable schedule of a planet crossing its star can signal the existence of other planets in that circumbinary system. The success of any of these detection methods hinges on numerous factors, including the planet's distance from the stars, its mass and radius, and the overall dynamic properties of the system. For instance, planets that are situated farther away from a star that is ejecting its outer envelope stand a much greater chance of survival. This is because they are less exposed to the intense blast of material being expelled from the star as it enters its red giant phase. When a star in a binary system expands into a red giant and sheds its envelope, the planets in orbit experience profound shifts in their gravitational environment and orbital paths. If the companion star begins to accrete this ejected material, its mass will change, which subsequently alters the gravitational forces acting upon the planets. These disturbances can destabilize planetary orbits, and the intense radiation released during these events can dramatically impact the atmospheres and surfaces of any nearby worlds. The ultimate destiny of a particular circumbinary planet is determined by the specific characteristics and dynamics of its home system. It is conceivable that some planets could maintain their orbits and endure these cosmic upheavals, though they would likely undergo significant transformations and adaptations in the process. A theoretical figure-8 orbit, where a planet weaves between two stars in what is known as a Lissajous orbit, is a fascinating possibility. In reality, however, such orbits are incredibly unstable and are not expected to persist for long in any real astronomical system, particularly for a body as large as a planet. There are several reasons why these looped orbits are so improbable. First, they are inherently unstable due to the complex gravitational interactions within a binary star system, where even minor disturbances can throw the entire configuration into chaos. Second, the gravitational influence of other bodies, like additional planets or asteroids, would actively work to disrupt such a delicate orbital path. Third, maintaining a Lissajous orbit requires initial conditions of velocity and position that are so exact they are virtually impossible to achieve naturally. Furthermore, the evolution of the system itself presents a challenge, as changes in the star's mass and radius over astronomical timescales would inevitably destroy any potential loop orbit. Lastly, the thermodynamic effects, including thermal and radiation pressures from the two stars, would also contribute to orbital instability and create an inhospitable climate on the planet. While scientists have observed small bodies like asteroids or comets in similar looping paths, these are always short-lived events. For planets, such an arrangement remains highly unlikely. Imagine if a planet were somehow positioned at the barycenter of a binary star system, the central point of mass, and managed to stay in equilibrium relative to the stars. This would represent a highly unusual and precarious situation. Theoretically, if the planet could remain perfectly stationary at this point, it might hold its position until the slightest perturbation or external gravitational force knocked it away. However, the probability of this scenario is vanishingly small for several reasons. To begin with, the barycenter's position is not fixed. It constantly shifts as the stars move in their orbits, meaning a planet would need to perpetually adjust its location, which is physically implausible without some form of external propulsion. Any minor gravitational tug from other objects in the system would easily dislodge the planet from this point. Fundamentally, being at the barycenter does not constitute a stable orbit, and the initial conditions needed to place a planet there in the first place would have to be extraordinarily precise. Lastly, the proximity to two stars would create extreme radiation and thermal conditions, further complicating the planet's existence. To put this into context, consider an imaginary world situated at the barycenter of the Sirius system. This barycenter is the point where the system's total mass is considered to be concentrated for analyzing motion and gravitational interactions. In the Sirius system, this point would lie somewhere in the space between the more massive star, Sirius A, and its companion, the far less massive white dwarf known as Sirius B. While a compelling idea, the dynamic instability and stringent initial requirements make the long-term existence of a planet in such a location a near impossibility. Should a planet be situated exactly at the barycenter of this kind of system, and if it were stable enough to hold that position, a scenario that is physically impossible for dynamic reasons, its inhabitants could perceive both stars as orbiting their world. For any observer on such a planet, the two suns would trace complex patterns across the sky, dictated by their orbits around the common center of mass. You would witness Sirius A and Sirius B in constant, though slow, motion against the backdrop of distant stars, with Sirius A carving a tighter circle due to its greater mass and proximity to the barycenter, while Sirius B would follow a much wider path. In reality, however, a planet could never maintain a fixed position at the barycenter of a binary star system. It would inevitably be subjected to the gravitational pull of both stars, which would draw it toward one of them. Moreover, the very presence of a planet at this central point would introduce new disturbances, altering the star's orbits and ultimately leading to dynamic chaos throughout the entire system. Now, let's turn to the more perilous aspects of binary and multiple star systems. The likelihood of a star absorbing one of its planets is notably higher in these environments compared to single star systems. This increased risk stems from the complex gravitational interactions and dynamic instability, particularly when the stars undergo various phases of their evolution. Several factors contribute to this planetary absorption. First, as stars evolve, they can gain or lose mass, either through accreting material or ejecting it, which alters the gravitational balance and the orbital characteristics of any nearby planets. Second, intense tidal forces between the stars and their planets can transfer momentum and energy, which can dangerously modify a planet's orbit and heighten the risk of it being consumed. Furthermore, when a star in a binary pair expands into a red giant or goes supernova, it triggers radical changes that can result in the engulfment of planets. General dynamic instability within these systems can also send planetary orbits into chaos, increasing the chances of either absorption or ejection into interstellar space. Finally, interactions with other planets or even passing celestial objects can disrupt orbits and elevate the danger. Considering these points, the probability of life emerging and flourishing in a binary star system appears to be lower due to a number of unique challenges. The presence of two suns introduces several specific obstacles that we should examine. For one, the gravitational complexity of these systems can disrupt planetary orbits, creating an unstable foundation for life to begin and evolve. Planets within binary systems often endure extreme climatic fluctuations because of the shifting influence of their two stars, leading to conditions that are hostile to life. These systems can also produce very high levels of ultraviolet radiation, which is detrimental to biological molecules and life-sustaining processes. Additionally, the powerful tidal forces from two stars can trigger intense geological activity and volcanism on planets, further complicating the prospects for life. Beyond these issues, the dynamic activity in binary systems increases the probability of catastrophic events, such as asteroid collisions or other cosmic impacts. The evolutionary stages of the stars, combined with their gravitational interplay, can also generate highly variable and extreme environments. This doesn't entirely rule out the possibility of life, as a planet in a stable orbit at just the right distance from two steadily evolving stars could potentially foster life. This remains a vibrant field of astrobiological research. The Sirius system's age is estimated to be between 225 and 250 million years, which is an exceptionally short period for life to arise when compared to Earth's timeline. It's widely believed that life on our planet required hundreds of millions of years to progress into more complex forms. In a system as young as Sirius, there simply might not have been enough time for such evolution to take place, especially since the planets themselves may still be in the process of formation and stabilization. The discovery of excess infrared radiation by the Infrared Astronomical Satellite, or IRAS, suggests the presence of dust or other materials like gas within the Sirius system. This material could have several different origins. One possibility is that it was ejected by Sirius during its own evolution, creating clouds of dust and gas that now encircle the system. For instance, matter that was lost by Sirius B could have been partially captured by Sirius A, or it might have lingered in the system, forming a disk or cloud of dust. Alternatively, this dust might have originated from the interstellar medium and may not be connected to the evolutionary changes of Sirius at all. Finally, if planets or protoplanetary disks do exist in the Sirius system, the ongoing processes of collisions and planet formation could also be the source of this observed infrared radiation. While the material cast off by Sirius B in its past might account for excess infrared radiation, other sources could also be contributing to this effect. Currently, Sirius A is in a stable phase of its life, fusing hydrogen in its core. Looking ahead a few billion years, once that hydrogen is spent, Sirius A is destined to expand into a red giant. However, it lacks the necessary mass to trigger a supernova explosion. Instead, following its red giant phase, it will shed its outer layers, leaving behind a dense, hot core that will cool over eons to become a white dwarf, mirroring the fate of Sirius B. The habitable zone, often called the Goldilocks zone, is the region around a star where conditions might permit liquid water on a planet's surface, a crucial ingredient for life as we know it. In a binary system like that of Sirius A and B, calculating this zone becomes far more intricate. The gravitational forces and thermal output from both stars create a dynamic environment, complicating the temperature conditions for any potential planets orbiting within it. Being substantially hotter and more luminous than our Sun, Sirius A's habitable zone would be situated much farther out than our own, likely beginning at a distance of about 5 astronomical units and stretching to roughly 10. In contrast, Sirius B, as a faint white dwarf, has a much lower luminosity, so its contribution to the overall warmth of the system's habitable zone is less significant. However, the presence of two stars means any habitable zone would be constantly in flux due to gravitational interplay and shifting levels of combined radiation. For conditions in the Sirius system to resemble those on Earth, a hypothetical planet would need to meet several demanding criteria. It would have to orbit within that habitable zone between 5 and 10 astronomical units from Sirius A. Furthermore, its orbit would need to be as close to circular as possible to avoid extreme temperature fluctuations, all while remaining gravitationally stable under the influence of both stars. Let's try to imagine the sunrise on such a planet, an experience that would depend entirely on the world's orbital path and axial tilt. As the much larger and brighter of the two stars, Sirius A would utterly dominate the sky. Its rising would unleash a brilliant and intense light, potentially painting the sky a bright, white-blue shade, a consequence of its higher temperature compared to our sun. The dynamics of these sunrises would be in constant flux, producing a spectacle of unique and varied astronomical events. Depending on the time and orbital positions, Sirius B might rise before, after, or even simultaneously with its brilliant companion. The interaction of their light could create intricate shadows and complex lighting across the planet's surface. This duality would also drive more complex seasonal cycles, as the world would be receiving radiation from two distinct sources with different intensities and characteristics. As a result, the celestial view from this world would be mesmerizingly unpredictable. There could be times when both Sirius A and Sirius B rise and set together, and other periods when they appear at completely different times. If a planet were in a circumbinary orbit, circling both stars at once, the habitable zone would be located even farther out to compensate for their combined heat, creating an even more alien and ever-changing vista on the celestial dome. We must also account for potential variations in habitable conditions, which could arise from the shifting distance between a planet and its two parent stars. When defining a habitable zone in a binary system, it's crucial to recognize that the inherent instability might render life-sustaining conditions less probable or less consistent over the long term. Theoretically, Sirius could experience a nova explosion in the distant future. This event could be triggered if Sirius B, a white dwarf, begins to siphon material from its companion, Sirius A, once Sirius A expands into its red giant phase. Nova explosions are a known phenomenon for white dwarfs that accumulate a sufficient amount of matter from a partner star. A nova is ignited when thermonuclear reactions flare up on the surface of the white dwarf as its mass nears the Chandrasekhar limit, which is roughly 1.4 solar masses. For a more cataclysmic supernova to occur, Sirius B would need to gather enough mass to actually surpass this limit, causing a complete collapse. However, given the current characteristics of the Sirius system, such a supernova event is considered highly unlikely. Therefore, while a nova remains a theoretical possibility, forecasting its specifics, including its likelihood and consequences, is exceptionally complex. The outcome would hinge on many variables, such as the precise conditions of the mass transfer and the orbital separation between the stars when Sirius A becomes a red giant. Due to its brilliance and proximity to our planet, Sirius holds a pivotal position in modern astrophysics as a subject of intense scientific inquiry. The star system has become a prime target for a wide range of astrophysical observations and experiments, which helps researchers better understand the structure and mechanics of both individual stars and binary systems. First, the investigation of Sirius A, a spectral Class A star, offers a detailed look into the life and evolution of stars. Studying it provides crucial information about fundamental stellar processes, including nuclear fusion and the generation of magnetic fields, which helps unravel the mysteries of stellar physics. Secondly, Sirius B offers a unique glimpse into the final evolutionary stage of intermediate mass stars. As a white dwarf, its study allows astrophysicists to learn about the structure, atmosphere, and magnetic fields of these stellar remnants, which is vital for comprehending the complete life cycle of stars and the ways in which they eventually die. Beyond that, the Sirius system is invaluable for the field of astrometry, which is the science of measuring the positions and movements of celestial objects. Accurate measurements of Sirius's location and motion provide essential data for calibrating astrometric techniques. As a binary system, it also presents a rare opportunity to observe direct stellar interactions, such as mass transfer and the influence of gravity on stellar evolution. The overall importance of Sirius in contemporary astrophysics is truly multifaceted, significantly advancing our scientific knowledge of stars and the cosmos. Research and cosmic experiments centered on this system are leaving an indelible mark on the field, broadening our understanding of binary star mechanics and the evolutionary properties of different star types. One of the central pillars of Sirius research involves observing its binary nature with advanced technology. Astronomers worldwide utilize space telescopes like Hubble, James Webb, and Gaia to perform precise observations of the dynamic between Sirius A and Sirius B. These studies help clarify how the gravitational dance between the two stars influences their individual structures, atmospheres, and evolutionary timelines. The magnetic fields of Sirius are another active area of investigation. Space missions outfitted with spectrographs and other specialized tools enable a detailed analysis of these fields and their effects on the surrounding stellar environment, including phenomena like coronal mass ejections and stellar wind. Furthermore, experiments are conducted to analyze the spectral signatures of Sirius, which provide additional insights. These spectral studies enhance our knowledge of the chemical composition, temperature, and pressure within the star's atmosphere, which is critical for deciphering its internal processes and physical characteristics. Because of its brightness and stability, Sirius also serves as an indispensable calibration beacon for a variety of space missions and astronomical instruments, helping to ensure their accuracy. Simulating the Sirius system is a highly complex task that combines the development of theoretical models with their practical application through advanced astrophysical technologies. The overarching aim of this modeling is to achieve a more profound comprehension of the phenomena occurring within this binary star system and to forecast its future trajectory. At a theoretical level, the process involves constructing mathematical and computational models that describe the physical interactions within the Sirius system. These simulations incorporate gravitational forces, the transfer of matter between the stars, orbital changes, and numerous other phenomena, all built upon foundational principles like hydrodynamic equations and gravitational theory. On a practical level, these theoretical frameworks are then rigorously tested against observational data gathered by telescopes and other instruments. A key component of this process is running numerical simulations using powerful modern computers to compare the model's predictions with actual astrometric measurements, thereby validating and refining our understanding of this fascinating stellar pair. By creating detailed models, scientists can experiment with a variety of parameters and conditions, allowing them to analyze potential development scenarios and rigorously test their hypotheses. For astronomers and astrophysicists, modeling the Sirius system is invaluable, as it deepens our comprehension of binary star dynamics, the complex processes at play within them, and the distinct properties of each stellar component, ultimately driving the creation of new astrophysical methods and technologies. The future of Sirius studies looks exceptionally bright, largely because of the rapid advancements in astronomical tools and techniques. These emerging technologies provide scientists with unprecedented opportunities to investigate this binary system with greater depth and precision than ever before. For instance, progress in radio astronomy and optical interferometry will soon enable far more precise observations, yielding data with significantly higher resolution to illuminate the intricate interactions between the system's components, its atmospheric processes, and its magnetic fields. Furthermore, the integration of quantum technologies and artificial intelligence into astrophysical research holds tremendous importance. Quantum computing promises to dramatically speed up the processing of massive astronomical datasets, while AI algorithms can help automate and refine observation processes to identify subtle patterns and anomalies. Simultaneously, advancements in spectroscopy and photometry will allow for a more profound analysis of Sirius's emission spectra, providing you with a clearer understanding of its physical characteristics, chemical makeup, and internal composition. We should also consider the evolution of space technology, which includes plans for new missions and telescopes designed to observe Sirius from beyond our planet's distorting atmosphere. By placing these instruments in space, you can eliminate the atmospheric interference that plagues ground-based observatories, resulting in the acquisition of much cleaner and more precise data about the star system. Now, if you were to dispatch our fastest modern spacecraft to Sirius, the journey would take a staggering 133,000 years. It's crucial to understand that the Parker Solar Probe's incredible speed comes from a gravitational slingshot maneuver near the Sun, a trick that is not available for interstellar missions. A vessel using traditional rocket engines, like Voyager 1, which was launched in 1977 and travels at about 62,000 kilometers per hour, would take approximately 150,000 years to make the trip. While that journey might sound impossibly long, a concept announced in April of 2016 offers a glimmer of hope, and I want to tell you about it. It's called the Breakthrough Starshot Project, an ambitious initiative from visionaries like Yuri Milner and Stephen Hawking, which aims to explore the nearest star system, Alpha Centauri, using ultralight microprobes. The core idea involves propelling a tiny spacecraft fitted with a light sail using the immense photon pressure from a powerful Earth-based laser array, theoretically reaching up to 20% the speed of light, and cutting the travel time to a mere 20 years. Of course, this project confronts immense technological and engineering obstacles. The challenges include fabricating a space sail durable enough to withstand the intense energy of the laser beam and survive incredible acceleration forces. Additionally, a sophisticated system for pinpoint navigation and reliable data transmission across such vast interstellar distances would need to be engineered from the ground up. To adapt the Breakthrough Starshot concept for a mission to the Sirius system, which is located roughly 8.6 light-years away, several critical upgrades would need to be considered. The light sail itself would require significant enhancement to make it more resilient against prolonged exposure to laser radiation and the solar wind. You could also explore supplemental acceleration methods for the microprobes, perhaps employing gravitational assists from large celestial objects, or even utilizing electromagnetic catapults for an extra boost. If we assume that these microprobes could be accelerated to 30% of the speed of light, the journey to Sirius would take approximately 28.7 years. This estimate is derived by dividing the distance to Sirius, 8.6 light-years, by the probe's velocity, which is 0.3 times the speed of light. After the microprobes pass the system, they would then transmit the collected data back to Earth. Considering the distance of 8.6 light-years, you would have to wait an additional 8.6 years for that information to arrive. When you add the travel time to the data transmission time, the total mission duration, from the moment of launch to the day we receive the first scientific results about the Sirius system, would come to about 37.3 years. It is important to remember that these calculations hinge on theoretical assumptions, and in practice, numerous challenges could potentially increase the overall mission time, as reaching Sirius and sending a signal home remains a monumental task. If you were to design a microprobe capable of sending signals to Earth from the Sirius system, you would face a number of immense scientific and engineering hurdles. The core issue is maintaining a signal strong enough to be detected across 88.6 light-years, cutting through the intense radiation from Sirius itself and other cosmic background noise. To achieve this, the probe would need a durable power source, like radioisotope thermoelectric generators or hyper-efficient solar panels, both designed to survive the unforgiving environment of deep space. The probe's transmitter and antenna would have to be engineered for maximum signal focus and amplification, ensuring minimal power dissipation over its vast journey. Furthermore, protecting the integrity of the information sent is crucial. You would need to employ advanced modulation and coding techniques to shield the data from cosmic interference, allowing for its recovery even if the signal becomes exceptionally faint. This is especially vital because the powerful background radiation from the Sirius system could easily overwhelm a less robust transmission. To ensure the signal is aimed precisely at Earth and nowhere else, the probe requires an incredibly accurate targeting system. It must also be shielded against cosmic radiation and micrometeorites that could otherwise destroy its delicate electronics. We would also need to account for the Doppler effect, which shifts signal frequencies due to the relative motion between the probe and Earth, by making constant adjustments to ensure successful detection and decoding back home. Overcoming the immense signal degradation across such a distance might even necessitate a chain of relays or repeaters positioned between Sirius and Earth to boost and forward the transmission. Here on our planet, we would require enormous receiving antennas and dedicated stations engineered to pick up extraordinarily weak signals. These facilities would need exceptional sensitivity and advanced noise filtering capabilities to isolate the probe's message from the cacophony of the cosmos. Executing such an ambitious mission would demand more than just cutting-edge technology. It would necessitate international cooperation and investments far beyond the scope of any single nation or organization, highlighting the need for a unified global strategy in space exploration. The scientific rewards, however, could be immense, as the potential for discovery within the Sirius system is incredibly promising. In the near future, we can anticipate a wealth of new insights that will refine our understanding of this binary star system.
Sirius offers a unique laboratory for observing high-energy processes in extreme conditions. The white dwarf, Sirius B, engages in intense gravitational interactions with its larger companion, triggering a variety of powerful phenomena like X-ray flares and thermonuclear reactions. By studying these events, scientists can deepen their knowledge of the physics governing extreme states of matter and the fundamental processes that drive stellar evolution.
To gather this information, researchers employ a range of modern techniques, including spectroscopy, photometry, and both radio and X-ray astronomy. The enormous data sets produced are then processed using artificial intelligence and machine learning algorithms, which help astronomers identify new patterns and improve existing theoretical models. In this way, Sirius serves a vital role in the astronomical community, acting as a crucial testing ground for verifying and refining our astrophysical theories. Beyond its scientific value, Sirius holds profound cultural and historical weight, having been one of the brightest and most recognized stars in the night sky for millennia. This celestial body has consistently captured human imagination, weaving itself into the fabric of numerous civilizations. For ancient Egyptians, Sirius was a manifestation of the goddess Isis, and its appearance was vital for predicting the annual flooding of the Nile, which sustained their agriculture. The ancient Greeks, meanwhile, viewed it as the loyal dog of the great hunter Orion.
For the Polynesian navigators, Sirius was an indispensable beacon that guided them across vast stretches of the Pacific Ocean on their long sea voyages. In Mesopotamian cultures, this brilliant star heralded the coming of the new year and its associated religious ceremonies. Across the globe, among Native American tribes, Sirius also occupied a significant cultural niche. The Lakota, for instance, saw it as a sign of approaching winter, while the Maya incorporated its movements into their intricate calendars and astronomical predictions. In China, Sirius was integrated into cosmological frameworks and astronomical calculations that were central to various dynasties. Yet perhaps the most astonishing ancient knowledge comes from the Dogon people of West Africa, whose understanding of the star system continues to puzzle researchers. The Dogon have long known that Sirius is a binary system, believing it has a companion star invisible to the naked eye. They assert that this companion, Sirius B, is incredibly dense and completes an orbit around the main star, Sirius A, approximately every 50 years. This knowledge is staggering when you consider that modern astronomers only confirmed the existence of Sirius B in the 19th century. Consequently, Sirius remains a majestic and mysterious object that has inspired, guided, and shaped cultures all over the world for countless generations. The question of paleo-contact, the theory that ancient human civilizations interacted with extraterrestrials from Sirius, is a frequent topic in speculative fiction, but is not supported by credible evidence within the scientific community. Nevertheless, the perplexing case of the Dogon tribe and their remarkably accurate astronomical knowledge continues to fuel debate about the possibility of ancient contact with civilizations from beyond our world. The prevailing view among most scientists, however, is that such astronomical knowledge was likely transmitted through direct observation of the heavens or via cultural exchange. The notion that extraterrestrials abandoned their home system because of a cosmic cataclysm tied to the red giant phase of Sirius B is certainly a compelling story. Nevertheless, it lacks any factual scientific foundation and cannot be regarded as proven by modern astronomy or archaeology, as the scientific community consistently relies on conservative, evidence-based perspectives. To conclude, I feel compelled to mention a scientist whose works, like Universe, Life, Intelligence, were written with such profound comprehension and love for the field that they can awaken a vibrant interest in astrophysics within anyone. As I delved into his writing, I was completely transported into a world of cosmic mysteries, exploring black holes, remote galaxies, and sprawling star clusters through his words. Shklovsky had an exceptional gift for elucidating complex concepts and theories, rendering them comprehensible and accessible to a very broad readership. This unique ability enables you to perceive the universe in an entirely new light and grasp the full scale of its wonders. The feeling of awe and curiosity his books generate can act as the ideal launchpad for a thorough investigation into astrophysics. This inspiration can motivate you to study new stars, galaxies, and a host of other celestial objects. Shklovsky perceived the cosmos as a domain of unending complexity, offering limitless possibilities for exploration and discovery. Let us uphold this wonderful tradition of communicating about the universe with sincere passion and in a language that everyone can understand.